We don't need a market for. We basically very cheap. Fresh code, very, very.
See, tomorrow will be the day. The Mexico has or not. So I feel like in Colombia we have
Good afternoon, everyone. Good afternoon, everyone.
Okay.
Good afternoon. Thank you all for coming. I just wanted to make a quick note that the level of whispering in the last few seminars has gotten a bit distracting. Because of the way the room projects sound, I can hear every single one of you whispering. Sometimes I can't tell who is, but I can always hear the whispering and it gets distracting for those of us sitting in the front. So please restrain from even a little bit of whispering, okay? Thank you very much. And it's my absolute pleasure to announce our speakers for today, Dr. Sobhy Masoud and Alex was just telling me that she actually did her bachelor's in Western in 2014. So it's absolutely a joy once again to welcome an alumni back to give a presentation. And we look forward to hearing about all the work you guys have been doing at Stevenson Engineering. Thank you.
Thanks, everyone. It's again a pleasure to be back again. I think the last time I was here before COVID, 3 years ago or something. It's always a pleasure to come back and see you guys and talk about some exciting projects we've been doing at Stevenson Engineering. We'll start soon. I just want to give you guys an idea about Stevenson Engineering. We're a structural company, consulting company that has been in the market for more than 50 years now. We've been doing all sorts of call it building projects, comes to residential, commercial. I think the highest we did in residential was about 9 stories. And remember the rest of the presentation we did way back here was about the wind challenges for tall buildings like that. But again, that's one thing we do, but at the same time, we're doing a lot of data centers, hospitals, schools, universities, you name it. And we've been really busy and like the fact that we've been in the market for 50 years, it's a testament that people really like what we're doing and we have a really good relationship with our clients. Toronto is our headquarters, but we also have offices in Ottawa and Calgary as well. And about 2 years back, we've been merged with a bigger company in the States, which is Salas O'Brien. It's a mainly mechanical and electrical engineering company, but now we're one team. We have actually now exposure even to work in the States. We have in total about 55 offices all over North America. And we keep now getting bigger and bigger and hopefully getting larger projects and having more diversity in what we do every day. So we like what we do. We always like the challenges and doing complicated stuff beside the usual, let's say, everyday bread and butter, simple stuff that we do. But we're here today to present some of these, we call it challenging projects and get you excited, hopefully, you guys, about it and hear your feedback about it. So Alex, the floor is yours.
Thanks. Thanks to everyone for being here today. I think the last time I was in this room, I was presenting my 4th-year capstone project. So it's fun to be back presenting a real project this time. So I'm presenting today Braddock Block 3. It's a commercial building located in Kitchener, Ontario. The main team behind this project was Perimeter Developments. The architect and prime consultant was Martin Simmons Architect. Hooper Construction was a general contractor, and us, Stevenson Engineering, were the main structural consultants. It's an 11-story concrete tower with one underground level for parking. We have a steel framed mechanical penthouse and a pedestrian bridge connecting to an already existing building. But the main feature, sorry about this.
Use the keyboard.
Oh, sure. Good idea. Okay. Okay, thank you. The main feature of this building is structural steel columns that support a sixth floor overhang of the corner of the building. So that was the main design challenge of this project. I'll get into more of the design and construction challenges a little bit later in the presentation. So the floor plan for this building, it's an office building. So we were able to use a pretty simple concrete column grid system, and all the levels, well, the underground level is parking. The first frame slab level is the ground level, and all the levels above that were typical office loading. Here's our 3D structural model. We can draft in Revit. And so that's where the program where all our structural sheets were taken from. And now I'll go over some components of the design. So first, starting from the bottom, our foundation was a wrap slab system. Typically in this type of project with concrete columns, we like to use concrete spread footings. However, the geotechnical report revealed that we had quite low bearing, only 200 kPa SLS and 300 ULS. And with our loading, spread footings just weren't an option. So we had to pivot and use a wrap slab. We use SAFE to model our wrap slab. So using the soil modulus, we were able to mimic the soil behavior under load. And then after we could evaluate the maximum pressures and compare those to our design limitations. So it's a bit of an iterative process to get our final thickness of our wrap slab, which was 1.8 meters thick. So as you can imagine, 1.8 meters of concrete is very thick. And this is one of our sections through our wrap slab. We had to step it down in certain areas to accommodate our elevator core, some pits, things like that. The picture on the left is our first pour. It was our concrete crane raft. And the picture on the right is actually standing in between the top and bottom bars of the wrap slab, just to give you an interesting perspective of the volume of concrete that needed to be poured. A couple more photos of the wrap slab through construction progress. Next, I'll talk about the specific foundations for our steel incline columns. So we continued the wrap slab into the corner where the steel columns were, and we used concrete piers at the base of the steel columns. So we broke it into 2 pours, and this was because we needed the top of the concrete pier to be at a very precise angle. And as you can see, we cast in place a red plate with anchor bolts with the second pour at that precise angle. And then when the steel columns, which were manufactured with the base plates on them, when they were installed, they could be installed precisely at that angle at the exact location we needed. So one of the construction challenges was how to get that angle precise. Means and methods were not up to us, but we tried to make the design as easy as possible so all the trades on site could work together in an easy manner. So next I'll talk about our typical concrete structure. We used concrete slabs, concrete columns, and our lateral system was concrete shear walls that were at the 2 stair cores and 2 elevator cores. And we used continuous draw panels as well to control some of our limits such as deflection and punching shear. Here's one of our slab designs. This was for the typical upper office floor. So this was above the steel columns. So our floor plan was the full rectangle, whereas below we had that, that corner cut out. One of the design challenges was when we were in the process of designing our slabs, we were requested to put a big opening just north of the elevator core. You can kind of see it there. This was for a feature staircase for the tenant. The issue with this opening is that it's oddly shaped and it's right in the middle of our 12-meter span. So deflection was a big issue here. So we had to go back and forth a number of times to kind of refine the shape. It used to be more of an L shape, which created more issues for us that we just couldn't work around. So we're able to reduce that L to a more reasonable size. And then we were also able to use more steel around the opening, compression steel, to reduce that maximum deflection. Some construction photos during the process of the concrete slab building. So on the left, that would be a pre-pour, like all the rebar is in place, and on the right, you can see the concrete columns and slabs all poured with those continuous drops around the perimeter and in the middle. So as I said, level 6 had that steel frame design, which met the top of those steel incline columns. So in the photo here, there's 6, and in real life, there are 6 steel columns. However, only 4 are actually structural. 2 are kind of dummy columns, like just for architectural purposes. The reason we only needed 4 is because there was only 4 concrete columns above that they needed to support. So those 2 extra columns we actually didn't need in terms of structural purposes. These are 23 meters tall. So it's quite a feature of the building. And from the underside, you can see we use steel framing, and then we use concrete on deck. So from above level 6, it's all uniform concrete. So these steel columns were actually only meant for gravity, only taking gravity loading. They're not a part of the lateral system. But since they're on an incline, have a bit of an angle, they do create lateral forces. So we had to design the steel beams to take those tension and compression forces to the concrete slab, which worked as a diaphragm to transfer those forces into our lateral shear walls. So that's how we resolve those forces. And so the columns could act only in a gravity. Some photos of further construction. So on the top left, you can see the concrete piers with the cast in place steel plate and anchor bolts. So as you can imagine, the 23 meters is very tall, and so the steel columns were manufactured off-site and shipped all together, as you can see on the right. These steel columns were actually pipes, big pipes they weren't specifically manufactured, or they weren't custom for this project. These steel pipes are actually used in industrial purposes, but we were able to purpose them for our structural use. And what made them unique to this project was the length. So they had to make 2 together, like to create that 23 meters. So one of the challenges in the shop was to make that weld seamless. So then visually it matched what the architect wanted. And the top and bottom of the columns were also manufactured in the shop. So the placement of these columns was also another construction challenge. So they used 1 crane to put the column in place. And on the right, you can see there's a second crane putting the steel beams in place as the columns was held there. So the top location and the bottom location were very precise. So that angle of the concrete pier needed to be perfect. Because if that angle's off just a little bit, you can imagine over 23 meters, the top of the column would be way off. And so those steel beams would no longer work. So that's why that precision at the bottom was so important. At the top of the steel columns, we used what we called steel baskets to facilitate the transition from the steel structure to the concrete structure. So that was one of our design challenges, as on site, the steel and concrete trade are different. So we wanted to make that transition on site as seamless as possible. So this basket provided that transition. So essentially, the steel trade would install these baskets where they had the anchor bolts already installed, and then they had threaded couplers at the bottom of the basket. So then the concrete rebar trade could come in and easily attach their rebar into that basket, and then the concrete pour could come in and pour their column. You're just showing the top sections are showing that concrete basket connection, and the bottom section shows a different type of connection we had to make, which was steel to concrete. So the level 6 slab was poured prior to the steel placement. So we needed to facilitate that steel to concrete connection. So we used cast in plate anchor bolts. Some photos of construction at the top of the steel incline columns. So these connections were for the structural steel columns, and for the 2 not structural columns, we just used a vertically slotted connection. You can see on the left, the deck under the concrete with the structural steel beams. And then on the right, there are the 4 structural steel columns in place, full height. And then the one in the middle you can see there is one of the architectural ones. The last feature I'll discuss is the pedestrian bridge that connects our building, the phase 3 building, to the existing phase 2 building. So the bottom left is the phase 2 building, and the top left is our phase 3 building. So that middle bridge connects the two. Phase 1 on the bottom right-hand side of your screen is the phase 1 building. You can see there's a bridge already connecting phase 1 and phase 2. And the top right is the phase 4 building, which is currently under design. And eventually it will also connect to the phase 3 building. So this whole campus will have connectivity in the end. On the right-hand side is a photo of the already existing bridge connecting the first and second buildings. So our intent was to match the design of this bridge. So it all looked, all the campus looks cohesive. So we utilized the steel Y-shaped column in our bridge. This was useful for us as we didn't actually connect the bridge physically to the existing building. We use an expansion joint, and so that Y-shaped column provided the bracing and the gravity support at the existing building end. And then on our end, we physically connected to our phase 3 building. On the right is a video of the installation of the bridge. So you can imagine it was also a challenge, kind of a constructability challenge, as the bridge was manufactured off-site and then put in place exactly. So they just had to go slow, and luckily it all went really well and it was installed without issue. One of the other design features or design challenges we had was the foundation for the Y column. We ended up using helical piers so we didn't disturb the foundations on the existing building. Otherwise, we would have had to interfere with those foundations, which just wasn't realistic at the time. Here's a photo of the final placement of the bridge. And actually a couple of weeks ago, we found out that this bridge won an award of excellence in steel construction from CISC. The category was architectural walkways, pedestrian bridges. And so this included us as the structural consultants, the architects, the steel erection company, and general contractors and developers. So the whole team was involved in that award. Here's a photo as of a couple months ago. So as you can see, all the steel elements or all the structural elements are in place. All the steel columns, the pedestrian bridge, all the cladding's finished now. So all the main structural components are finished. So now they're just working on the rest of the building, the electrical, mechanical, the tenant fit out requirements before occupancy. Are there any questions?
Actually, I have a question. Are the structural columns also connected with an angle, or is just?
Sorry, can you speak up a little?
Yeah, sure. Are the structural columns also connected with an angle, or it's just I'm seeing like in the pictures?
They're actually at an angle. Yeah.
So the common joke is that architects always want engineers to magically defy physics. Do you get a lot of that?
Yes.
Yeah.
I've joked with coworkers that they want floating things, and we can't make floating things happen. So they were pretty insistent on this kind of feature. So yeah, we made it. Yeah, it's pretty neat feature. So it's pretty unique.
You said that there are like structural inclined columns and then the non-structural ones.
Yeah.
How did you ensure that they don't carry like gravity loads?
Yeah, so at the top of the non-structural ones, we use a vertically slotted connection. So it actually allows a little bit of movement at the very top. So then the gravity load doesn't actually, will never reach those columns.
And also for lateral loading, because all of them are designed just for gravity loading. Is there also like, how did you isolate that as well? Or are you saying that during seismic events, they would fail, or?
No, so
Not both.
in level 6, if you remember that tension and compression flow diagram, the diaphragm of level 6 resolved those lateral loads.
So, okay.
Those incline columns have an additional P delta effect, and did you have to reinforce the anchors because of those extra moments?
Yeah, so when we did the lateral model for that, the gaps model, it included the bigger effect. So any magnification for the moments, or like any extra, say, moments or deformations have been already taken into account. But I'm bigger than the bigger but for something like this, it's definitely very important to use it. Yeah. So,
Thank you, Alex, for the interesting project. I would like to start first by offering a bonus mark for one of my students. And actually, the presentation is perfect timing, because like I'm teaching graduate course now, finite element methods. And their final project is to model the high-rise building in ETAPS. So they thought that I'm challenging them, but it's beautiful that they see now how civil engineers, they have to accommodate the architectures.
Oh, yeah, we have ETAPS model for every project.
I even mentioned in my last lecture how we always fight with architects, but that's fine.
Yeah, it's always a back and forth. It's good to get ahead of it in the initial conversations.
Very challenging that you have those inclined columns which is supporting stories on the top, but Kitchener is not a high seismic zone. So I'm assuming that the governing lateral load is wind, but in high seismic zone, how this is going to change the design?
okay, like when we model this, when you look at the lateral force, is it wind or seismic, whatever is controlling? Again, it's a lateral force, so it doesn't really matter. But if it's high seismic, we might get more issues that could be as maybe more complicated conditions. But at the end, it's like for, let's say when you're working in Ontario in our area right now, like where seismic is not really a big issue, there is not really much challenges. But if I'm building this in Vancouver, we might have to consider from other things for connections. Things like that.
Because the detailing here really matters in the connection that from action at this floor, yeah.
But at the end, these are carrying gravity only. Like as Alex said, all of the tension, compression forces resulting from the slope are resolved in the diaphragm. Okay. So at the end, this is taking on the axiom. So the connection between the column and the level 6 slab has to be able to take all of these tension, compression, like diaphragm forces. So if you're, let's say, in an area that's, let's say, seismic issue, these connections will be more complicated than something like that.
This was my question, because
But at the end, okay, the lateral, which actually the question that came from other, like the other side there, lateral is a function of the stiffness of the element. So at the end, these are tiny columns, and the actual because of they are tall, they are very slender, they wouldn't attract much lateral energy. Okay, but the lateral will be attracted more to the shear walls.
but the issue is the rigid diaphragm action.
Exactly, yeah. But the thing here, we have a concrete deck. Yeah. So, and it's only a small area, like you see, it's only within the footprint with the 6 columns up. So we have the rigidity there. Yeah. But if it was, let's say, a bigger plate, let's say we didn't have, if it's a shallow concrete deck that here we had, it was, if I'm not mistaken, 7.5 inches, like 1.9 in total. So we had a lot of concrete to do the diaphragm.
What's the connection between, because I believe that the steel columns are supporting kind of steel structure, and then you have concrete diaphragm. So the connection between the 2 floors, what's the?
Yeah, there are rebars in between connecting them. Like when that diagram that Alex showed with all of the forces, because these lateral forces has to go to the core at the end. So it has to travel through the concrete slab. So had reinforcement to take care of that. Yeah. Like they weren't just 2 isolated pieces. It has to be continually reinforced.
Are the inclined columns at risk of buckling or torsion because of their geometrical?
So I think that was part of the design. It's like the way these are like they look, they are very tall, they look slender. Like they have been designed to make sure we don't buckle or anything like that. That's for sure. Like these are actually very massive columns, like 860.
Wonder as they present.
Yeah, and just in a because they are looking 23-meter high, so it just deceiving when you look at that. No, they are very thick columns. Any other questions?
All right, so we over to
Okay.
you.
So we'll jump to the other half of the presentation. How much time?
15.
Oh, okay. So I'll be talking about another project that we did. Just actually, this project was finished just last summer. It's a different type of jobs. Like this is not call it a building, which we do call it 90% of our buildings. This is a transit job. Okay, so this is Rutherford Post Station. I don't know if some of you guys might be familiar already with Toronto. We would have these GO stations for commuters going all the way to Toronto Union Station and they go to their offices. So this one actually is with one of the lines coming into Union Station. Rutherford, this is an existing GO station already in Vaughan. And that station, Metrolinx, which is the owner of all of, or the main client of all of these stations, which is a crown agency for by the federal government, they basically wanted to improve that station. So that station basically didn't have enough parking. It had only one platform. There wasn't like just two tracks with one platform. There was no other platform, just on one side only. So they wanted just basically to improve it. So this job, it's a P3 job. So what is P3? So in all of, let's say, our daily, the project that we do every day, let's say we get hired by a client or a contractor or an architect. It goes through, let's say, some RFP or request for proposal. We put a pricing and they choose a team based on cost and qualification, things like that. These governmental jobs, or call it infrastructure jobs, are more complicated. These are really big jobs. We're talking about $500,000 to $1 billion, like a hospital or a transit station. So it's a big risk for the government to just say, okay, this team will do it. So what they do, we go through something called public-private partnership, P3. So it's basically a procurement method where the Infrastructure Ontario, which is the government in that case, and Metrolinx, are hiring 3 teams. Okay, these 3 teams will work for a certain period. The team will be a full team: contractor, architect, structural, mechanical, unit, technical. And these guys will be working, let's say, for a year, and they come up with a design at the end and the cost and the schedule, and they present it to the client, and then the client will pick the best of them. The best can be maybe the cost or the schedule, and then that one team will be the team who will carry over after that. Okay, so basically 2 guys will lose, or 2 teams will lose, and 1 team will continue. It's a big risk even for us as consultants, but these are really large projects, and it's really worth the risk to do that. And there is no other way. Let's say if you want to do a hospital or a big transit project, there is no other way. That's the only way so far that the government has. So what does this mean? So during design, like during, let's say that, okay, let's say a year of design, we're all working hard as one team, and there are other 2 teams are working, coming up with all of the ideas to improve in cost, to improve in schedule. Because you don't know, you have to really work hard with innovations and ideas to be the winner at the end. And most actually the cost, we're carrying the cost on our own. Like the government would pay us something, but not enough to cover our costs. So there is even also a risk here that if we lose a job, we're losing also on our bottom line and our finances. So, and during that time, ideas can change over time, so you can keep repeating design. Everyone coming with an idea that contractor say, like, it's better to do it this way or better to do that. So it keeps changing. But we've been doing this for a number of, like, at least 2 decades now, and we've been familiar with the basically the procurement. Now, let's talk about the project itself. So the project, you can see here this area view. This project is completed now. So this was a rendering way back. So it's a $240 million contract. It has a parking garage component, which you see over that 6-story parking garage, because that was one of the purposes. There was not enough parking, and it was a problem for commuters always. They couldn't find parking. I remember when I was working downtown years back, I got tickets many times because I couldn't find parking. So, yeah, so that's 6-story parking garage. And also all of these, the platform on this side, that was an existing platform. They wanted to improve. And we built a new platform on the other side. And we basically connected them with tunnels below the railway. And also to go from the garage to the other side, we have to connect them with a bridge over the railway. And there is a lot of other canopies and things like that. Okay, so we'll go quickly through the components of the projects. So this was the team, Elisdon was the builder, which Elisdon was actually, they started here in London. They are basically the second top contractor in Canada now. And they started here in London decades back. And Metrix, the owner, Morgan Bereni, that was the consultant for M&E. And he also was an M&E. It was a big team. This is just some of the names. So we'll talk about the parking structure. So the parking structure, it's a 6-story, as you see here. It actually had some solar panels on the top. It was a precast garage. When we design precast, it gets a little bit complicated in terms of we design foundations, we design lateral system, like we are at the end, the engineer of record. But we get a precast engineer who will design all of these precast elements. So these are basically, when you look at the floor plan here, I think this was about 18-meter clear span for the cars to go through. So these are pre-stressed double T's to basically be able to span 18 meters or 60 feet. And precast columns, precast, we put it here, inverted double T's with the precast double T's would sit on, which you will see usually whenever you go to a parking garage. And we had the lateral system, we had shear walls here. These were cast in place, okay? So these were not precast. Now, so the footing was a challenge. So Alex talked about in the Kitchener job that Alex presented, we had only 200-300 kVA soil capacity, which is not enough. This is a precast concrete garage, is very heavy for 6 stories. So again, we got a 200-300 kVA, which wasn't good enough. So we're thinking about foundation, which is expensive. So there is a technique, I'm not sure if you guys have heard about that, but there's a technique that's happening, been now being implemented in a number of projects called soil improvements. So basically, you improve the soil. That's actually some geotechnical consultants or geotechnical companies, they are expert on that, will basically improve the soil to give you higher bearing capacity. So through that, we had the company who did the work at the Ed Keller Foundation, were able to give us 200, 300, give us 450, 600, which was really good to still go with the spread footing. And this was cheaper than going with caissons. So ended up with that. But the design was for this, call it soil improvements, the design foundation, it's very challenging because we have, as structural consultant, we have to go back and forth with them, including the loads. They give you, call it the stress contours below grade, and then they will give it back to you, to the consultants, and then give it back to them. It requires like a lot of iterations back and forth, because they have to improve the soil very specifically where you need it. So it's a very, call it, delicate or the technique, sorry, that you may want to make sure that you're getting the soil improvement where you need it. Anyhow, so it was a back and forth between us and them. Eventually worked it out. The precast, as I said, it was done. There was a precast engineer that we've been working with. And you can see here during erection where the precast have been going up. And what you see here, these are the shear walls that were cast in place. Now, so that was the first component. The other component is the station building, where people go and get their tickets, buy tickets before going to the platform. That station building was a single story. It wasn't complicated. A steel building. We went with the steel for that. Like the majority of the elements in the station was steel. The challenge with that, it was just adjacent to the parking garage. And there was basically some, call it fire separation issues due to put, like it's a little bit complicated. So at the end, we had to basically a single story building and just do a roof, like a metal deck roof. But in that case, we had to do a concrete on metal deck for these fire issues, which is not really normal for a single story building. Now, the platform structures. So as I said, we had to do some improvements for one of the platforms and build a whole new platform on the other side. So the improvements meaning putting new platforms. So we ended up with putting all of these steel columns, the steel canopies through the entire platform. You're talking about these platforms are about 80 meters long. So I think we covered about 60 meters of that. And they were like the columns were every 4.5 meters in center. And there was some of the challenges. You see something called LCS allowances. The government is looking into the future of electrifying all of the trains. Like the trains now, they just running fuel. But in the future, what the government will do is to make all of this electric. That means you will see soon in the future some, okay, I don't know how soon it is, but you will see all of these stations along all of these tracks, like wires, electric wires, where these trains will get the power from. So they are basically, when we're building that station, you want to plan ahead for that. So there we knew from the owner where these future columns will be there in the future and what kind of loads we're getting. And we have to design for them and include them in the design of these canopies and these columns. So some of these columns you see here will be reinforced to accommodate what will happen in the future. Now, for the new platform on the other side, so for people to go from this tunnel, from this platform to this platform, you can either go through the parking garage, take the bridge, or you just take a tunnel. So we had two tunnels, and we had to basically build this was concrete. They were actually precast tunnels, and you can imagine how we designed for all of the rail, the train loads, and we had to design on each side the stairs and elevators that will take you to that tunnel. So you can imagine the design of those were definitely very complicated, and we took all of the provisions of the earth separation and things like that, and then you don't see them because they are below grade. Now, there was also some site work. We had two small pedestrian bridges that would take you again from the garage. But these are on grade, so you wouldn't really know there is a bridge there. And we had to design those actually to the highway bridge design code, which was sort of insane because they are just 9-meter bridges. And then we had also to do some canopies on bus loops. So for the buses, when you see here when the bus is coming to the station, we will need canopies above them, so we designed all of that side. Now, that last piece, similar also to what Alex showed you about the bridge connecting the two buildings. So here we had an overhead bridge that's connecting the parking garage to the west platform. So where people basically can cross to the further platform. That's what the big bridge. This was a 45-meter bridge. The idea about that bridge, the way we did it is, it has to, okay, it's above the railway and we need to some clearances because again, the trains that running below that bridge in the future will have all of this electrification. So we had to make sure the bridge is above all of this, okay? So basically Metrolinx give us all of the requirements, how far we need to be above the rail. So it's not only just the height of the train, we need to be way above that. So what you see here, this is the bridge configuration. It's a truss on each side. And that truss basically is what's spanning. So the truss is carrying the floor below, carrying the roof above, and the truss is taking that gravity load in even lateral load to one side here. This side is where the parking garage is, when you're coming from the fourth floor. On the other side, that side where we call it a stair tower is, This were the parking garages, and actually we kept it isolated. So if you remember what Alex presented, Alex showed a bridge that was isolated from one end. It's not connected to the existing building because you don't want it to mess up with the lateral system of that existing building. So again, here it was the same idea. So the parking garage was here. It was fully separated. And we had a column, was about 12 meters from the parking garage to carry the gravity load. And we built the full structure on the other side of the platform to carry the bridge and take the lateral forces. We call the stair tower. So this is the stair tower, which is on the platform that you see here. This were all structural steel, was I think 3 stories high. This tower had to be designed because it's sitting on the platform. There was some basically concerns about peer protection. What if a train derails out of the station and hit the tower? That means the bridge would collapse. So we had to take some of this into design. Now, the bridge itself. Okay, so this is where I will end up that video. But that bridge was basically installed in pieces, and actually it was installed on the side. It's a 45-meter bridge. Okay, it's almost 50 meters. So you can imagine to transport these 2 big trusses with the deck, it would be impossible. So what the Elliston, the contractor, did, it was fully assembled on site in 2 pieces. And actually they did all of the electrical, mechanical, all of the services, ceilings, whatever they can do on the ground, they did it. Basically to minimize, you don't want people working on top of the bridge, like whatever you can do on the ground is always easier. So they did this on an area in the side into these small pieces, and then they splice the bridge together. Now, to lift the bridge, there is not much of a luxury here because these trains are running all the time. And it's not only the trains for the commuter, there are also the CB rail trains for freight, which is they run all the time. So the contractor had a very limited time schedule or an opening, which is only working during the night from I think midnight till 6 or 5 in the morning in a weekend to get the bridge on basically lifted. So actually I was there. Let me see that. I'll show you guys the video. To show you how complicated it was to raise. So I think that I took that video, I think it was 1 in the morning. And you can imagine the whole team and safety and all of the precaution that if anything goes wrong, it will be a disaster. Like it's a very heavy bridge, and we had actually a special crane to lift it. And as you can see here, all of even the finishes for the bridge is already there. Okay, like you can see this below the bridge, the soffit it's all already finished. Okay, because you don't want to do this work above the train. Okay, so this is the parking garage on that side, and that's the steel column or the steel basically support that on the side of the parking garage. So you'll get some people talking in the ground. And yeah, on the other side, that's the stair tower that I was talking about on the platform, which is the new tower. So you can imagine how slow we have to basically rotate something big like that and make sure it fits between both sides. just running it quickly. Which is a very slow process. And I think they were almost there, like. I didn't sit down until there, because it was already late at night. I didn't want to stay until the basically fix it, but anyway, that by I think 5 in the morning, everything was set. So again, that's the Rutherford Go Station project. And yeah, please feel free if you want to take the train at one time and visit it and have a look, that would be good. Any questions? For both projects? Do you have time or?
Yeah, maybe 5 minutes.
Yeah. So now, if you have any questions, please feel free, like for this project or what Alex presented. Okay. Question? Yeah, it's a question. Yep, go ahead.
So for this project, like you were talking about how difficult it is to do the prefabrication and installing it. But if it's possible, then would that be the recommended route? It's better to do it in site. If it was possible, like the track wasn't on the way and stuff.
Yeah, okay, yeah, that's actually all of the. It will differ by a project, yeah. It depends on the location and the site and what are the constraints. But most of the time for something like this that you want to put on top of a railway, definitely fabricating it. It doesn't have to be inside, maybe fabricating it on the shop, but it has to come into pieces. They here took the option of doing it on the side, but they had the room to do it, and they're putting it together. But maybe on another side, you didn't even have a room to put it there. So you have to do it completely in the shop and come in small pieces that you're connected on the side. So again, it all depends on the logistics and what's happening with the project. Yep.
How did you select the pick points for the bridge when lifting it?
Oh, that's a good question. Very smart question. Yeah, so basically the steel trade or the steel contractor workers, so that they sent us a couple of options, how they wanna basically lift it. And we basically had to study this because then during lifting, the stresses or the forces are completely different than the final condition. So I had to actually go back with them back and forth because at the end, you don't want to beef up the bridge for only the sake of lifting it. Okay. Maybe if you have to, you have to. But at the end, we didn't want to change the design from the final condition. So basically, you have to lift it in a way the forces are not more than what we have. So we did a couple of iterations, and I think at the end it was lifted from, I don't know if you can see that. I think 1 point here, 1 point there, and so basically you have 2 cantilevers of the edges. That's the way it was done. But we checked it to make sure the forces are fine. Yeah, really good question. Yeah.
In the P3 contract, unlike the TB contract, how the client manage the contract administration with quality assurance of the construction process
The contract administration.
and the quality assurance of the construction process?
Yeah, so okay, the whole point about this P3, the way the government chooses this, and they like to do with the P3 is all of the current liability on the builder. So the builder or contractor in that case, they are taking all of the liability in their hands. So quality assurance, contract administration work, but it's not the contractor and all of the consulting team. But at the end, the contractor or the builder has the full responsibility to give the client a product that had with all of these quality issues. And actually there are different models for that. Like it can be only a design build, or can be a design build finance, or can be design build finance and maintain. So if it comes even to maintaining it, that means the contractor will be taking care of the project, let's say for 10, 20, 30 years, which actually happens in hospitals. So that means they have to be very sure that it's in their own interest to make the product good, when they will be maintaining it for the next 30 years. So it comes to, it's a risk on the contractor, and that's why the government now like this system, because they are actually taking it away from their hands. It's answer the question.
I think please come down if you want to have further discussions afterwards. I think people probably have to go to class. So let's thank our speakers once again so much.
I was here at the grant.